So let's begin by talking about exponential growth. Now, we dove into this a little bit the other day by playing with the graphs a little bit. So I'm going to give you the basics again. It's in the exponential growth functions look like this, where they have y equals a times b raised to the x power. Okay, and this we're talking about exponential growth. If we're talking about exponential growth, the a plays a role. Remember, it has to be greater than 0, and this is our initial amount, the amount we start with. Okay, b plays a role, and if we're talking about exponential growth, then the b is going to be greater than the value of 1. Okay, greater than the value of 1, and that would be our base, and this is also known as the growth factor. So whatever that happens to be is growing by a factor of b. Now, on a side note, we should also keep in mind that whenever we have exponential growth, okay, the shape of the graph will look something like this. It will be going up exponentially from left to right. And remember that the graph of exponential means that for equal distance of x, I am getting equal factors of growth. Remember, so equal distance of x, I get equal factors of growth for y. So the graph will look something like that. All right, so here's a setup for one of the problems that we would see regarding exponential growth. So it says, since 2005, the money that we have spent in America on restaurants has increased 7% a year. So we know that in 2005, we spent $360 billion out at restaurants for the year in the United States. Okay, so the Census Bureau keeps track of that, or maybe or some kind of a private fund keeps track of that. So we have this data, and we want to be able to model this data using exponential growth. So how do we model this data using exponential growth? So we're going to begin by saying, okay, y is equal to a times b to the x. We need to make sure that we understand what each of these variables is going to do or represent. Okay, so let's talk about over here. What's the y part going to give me? I'm going to write an exponential function that tells me what when I'm all said and done. So what should the y represent? You know, amount spent. Yeah, very good. So let's make sure we understand what each one's going to be. So amount that we spent. Okay, amount spent. Okay, the a part. What does that part represent? Yeah, that's our initial amount. Okay. Very good. What's our b part here? Where's that part? What's that going to be? This is our growth factor, right? Okay, and then what's the x part going to represent? Yeah, years since when though? So when are we starting this? Yeah, years since 2005. So before you start a word problem, it's really important that you can identify what each variable means and represents in the problem. You should be able to say to yourself, okay, y is going to represent my answer I'm looking for, a is going to represent my initial amount, b is going to represent my growth factor, and x is going to represent number of years since 2005, because that's where we're starting from. So that process that we just did is probably the hardest and the most important process. The rest of this stuff is just calculator plug and chug, right? So if I'm going to create a situation that models this, I'm going to have this. I'll go in purple. Y is equal to, my initial amount was 360 billion. All right, so I'll leave it as 360 billion. We should also remind ourselves that we're working in billions, right? Okay, our growth factor is 1.07. Where in the world does 1.07 come from, and why did I write it like that? Yes, Brandon.
0.07 is just your 7%.
Very good. The 0.07 represents the 7%, and I'm growing 7% on top of,
The 100% that you.
yes, very good. So that represents a 7% growth. Does that make sense? If you just put 0.07 in there, you're going to end up with an answer smaller because your growth factor is less than 1. That make sense? Okay, so that means that when you're taking a growth, you have to take that into consideration, okay? Now, x is just x, and that's years since 2005. So now let's say that, okay, so let's use this model to predict how much we have spent in the year 2015. This is classic mathematical modeling, right? We're taking some information, some data that we know, we're applying everything we know about exponential functions, and then we're using that data to create an answer for us to seek into the future, all right? So if the data holds true to the trend of exponential growth, we should be able to get pretty close as to how much we're going to spend on restaurants in 2015. So I want to calculate this, all right? So help me calculate it. I'll use orange. So I want y, the amount we're going to see spent in the year 2015. So 360 billion times 1.07. Okay, now think about it. Years since 2005. What would that be? What's my exponent? 10. Very good, because I'm saying years since 2000. So I'm going to have 10 up here. Okay, good. I need to run this through my calculator. So I'll show you how to do this. Take your calculators out, and we'll make sure we can all run this through our calculator. All right, here we go. So I'm on the blank home screen here, and I want to run this 360 1.07 to the 10th power. So here you go, 360. Parentheses, I'm really just going to enter it in just the way I see it. I'm going to go 1.06, or sorry, 07. And then I'm going to do a caret. Okay, and notice when I hit the caret, it gets me up to that exponent, and my exponent is 10. Now before I hit the enter button, what would we expect to see? A number more than 360 or less than 360? We would expect to see a number that's greater than 360. So if we don't, we maybe did something wrong. So here we go, 708. There we go, 708 what? Elephants? Monkey? What is this? $1 billion. Yeah, there we go, okay. So we're expecting about 708 billion in the year 2015. That's our estimation. Alright, so exponential decay looks a whole lot like exponential growth, except instead of a growth factor, we're going to have what? A decay factor. Very good. So we're still going to have A is still going to be greater than 0. Right? It's still going to be greater than 0 for exponential decay. B is going to be now stuck between 0 and 1. Alright, so our decay factor is between 0 and 1, meaning that we're growing less than 100%. That's why we want that number between 0 and 1. And then, of course, x is our output. Okay. Now, every single graph that models exponential decay is going to look something like this, right? It's going to go down from left to right. So as x increases, y decreases exponentially. That's called exponential decay. The same rules apply for exponential decay, meaning that equal growth gives you equal decay factors. Equal growth in x gives you equal decay factors, okay? Okay, here's a very abbreviated handwritten version of the problem. Let me say it out loud so you guys can hear. So let's say we buy a car for $20,000, which you could buy a brand new car for $20,000 today. That's not, something. According to the problem, it says the value of the car decreases 20% per year. I don't know if that's true or not. It seems a little high for me, but we'll just go with it for the sake of this particular problem. It decreases at 20% per year. After 6 years, you want to sell the car, okay? And the sticker price is $4,000. So if you're the seller, is that good or is that bad? So we're gonna figure that out right now, okay? And if you're the buyer, would it be good or bad? So take a guess right now. I think that's a good deal or a bad deal for the buyer. If you're the seller, sorry, if you have the car and you're selling it, is it a good idea to sell it for $4,000 or a bad idea to sell it for $4,000? Just take a guess. What do you think? Bad? You think it's a bad deal? Good deal? Okay, so we're kind of mixed in between. Okay, so let's go ahead and start with what we know. We know we're going to have exponential decay, a times b to the x. A is our initial amount. So what's that going to be in this particular case? $20,000. That car cost $20,000. All right, now our decay factor is going to be 1 minus 0.2. Okay, right? We have one plus our decay factor, we have 1 plus our factor for growth. We're going to have 1 minus our factor for decay. Does that make sense? And then, of course, we have to the x power. So that's really 20,000, right? What's 1 minus 0.2? $1 take away 20 cents. How am I left with? 80 cents. I'm left with 80 cents. So 0.80, all to the x. You see where that came from? Yeah. Good. Okay, and then how many years later is this? That's equal to 6. Okay, so 20,000. And then I've got 0.8 all to the 6. Why don't you guys go ahead and compute that for me and tell me what you think that car is worth. Will says $5,242 and then 88 cents, something like that. Okay, so I'm getting that as well. So what do you guys think? Is that a good deal or a bad deal if you are the seller of the car? That's a bad deal. What if you're the buyer of the car? That's a good deal. So depending on who you are, that's what you get for that one. Okay, compound interest. We already studied simple interest. That's kind of like where you go to your uncle and you're like, hey, uncle, I need to borrow $100. He's like, okay, but I'm going to charge you 10% interest. So that's like a one-time thing. So you end up paying $110 back, you know? That's simple interest. Compound interest is much different. Compound interest is interest that is computed on top of other interest. Does that make sense? So interest computed on other interest. So the way that we calculate interest is through this formula here. Okay? 1 plus r over n all to the nt. So let me tell you what each of these pieces mean. This is a very, very useful and important formula for compound interest. Let me move up and over. What do you think the A represents? Yeah, that's your amount that you're going to get at the end, or how much it's going to be worth at the end. What do you think the P represents? The principal. Okay, the principal means how much you start with. Okay, the principal is maybe like your initial amount. Okay, that's your initial amount. The R, what do you think the R is? That's your percentage rate, but it's expressed as a decimal. Okay, so if you have a 3% rate, the decimal will be 0.03. So your rate is a percentage represented as a decimal. What do you think the N represents? This is the thing that separates compound interest versus simple interest. The N represents the number of times you compute or compound per year. Okay? And I'm going to go ahead and give you the breakdown of this. If interest is computed annually, how many times a year do you compute interest if you do it annually? What does annually mean? It means once per year, 1 per year. So your N would be 1 if you're compounding annually. Does that make sense? There are other ways to compound interest. The second way is quarterly. So if you're compounding quarterly, how many times a year would you compound something quarterly? 4 times a year. So your N would be 4. Oops, that's a Y. Your N would be 4 times per year. The other way, another way that the book shows us is monthly. So what do you think that's going to be? Yeah, your N is going to be 12. That's an 11. Okay, 12 times per year. Now there is also biannually, there's also daily, there's also continuous. But this Algebra 1 course focuses on these 3 right here, annually, quarterly, and monthly. And you need to know that if you see the word annually, your N value is going to be a 1. If you see the word quarterly, your N value is going to be a 4. If you see the word monthly, your N value is going to be a 12. So far, so good? Stick with me. Okay, the other thing that we haven't talked about is the T. What's the T going to represent? Time in what? Minutes, seconds, leap years? What?
Years.
Time in years. Okay, the time is in years. So the compound interest, meaning interest applied upon other interest, is calculated P times the quantity 1 plus r over n to the nt. Alright, let me give you some examples of how this works. Alright, let's compare these 2 examples here. So we want to compute the amount that we're going to have at the end of a certain time frame. The first example is, let's say we're going to have $4,000. We're going to invest $4,000, 6% rate of return for 5 years, compounded annually. 6% is really good. I don't think you find that anywhere, but we'll just go ahead and play with it. So here we go. We know the amount at the end is going to be P times 1 plus R over N, all to the NT. So let me go ahead and walk you through this, and then show you how to plug it into your calculator. Make this a little smaller so we can see. So the amount that we're going to get at the end is going to be the principal, which was $4,000. That's what we're starting with. Okay. I'm going to have 1 plus. My rate is 6%. So I'm going to write it as a decimal, which is 0.06. I'm going to divide by n. N is the number of times that we compound per year. In this case, it's annually, so my n value will be a 1. And I'm going to raise it to the n times t. So that's just going to be 1 times t is the number of years, which is 5. So let me show you how to compute this in your calculator with the proper keystrokes. So take your calculators, put it to the side, and here's how you would do it. I'm going to type it in basically just how I see it. So I'm going to go 4,000, and then I'm going to go parentheses, and I'm going to go 1 plus. Now because I'm dividing by 1, I don't need a second set of parentheses, so I'm just going to say 0.06. And then my exponent, I can do 5 times 1 in my head, that's just 5. So I can have that exponent of 5. So will we expect this to be more than or less than $4,000? We would expect more than, right? So if we hit enter, and I'm seeing $5,352.90. Okay, 5,000, let's go ahead and write that down. So the amount is approximately $5,352.90. Okay, now let's compare that to this example over here. A is going to be P times 1 plus R over N to the NT. So the amount that we're going to get, the principal, I'm starting with $500. I'm going to have 1 plus, my rate is 4%, so that's going to be 0.04 divided by my N. My N is quarterly, so what number pertains to quarterly? 4, very good. All to the 4 times the number of years, which is 6. Alright, so let me show you how to plug this one into the calculator. So I'll clear everything for you. So here we go, $500, my initial principal. I'm going to multiply this by 1 plus. Now at this stage of the game, you need another set of parentheses. So you're going to go parentheses and go 0.04 divided by 4. Okay, and notice I'm closing this set of parentheses corresponds to the 0.04 over 4. I need to close my parentheses again to complete everything that I have. Hold on one second, it went away from me. Okay, there we go. Oh. Sometimes it jitters away. There we go. Okay, I'm back in business. So now, notice that the 0.04 divided by 4 is the 0.04 divided by 4 in its own set of parentheses. Then you go caret, and then I can do 6 times 4 in my head, that's 24. So now that I've entered it correctly, now I ended up with 634.88. Or 87, sorry. So how much did I make just for letting my money sit there? No, I didn't make $634. How much did I make just for letting my money sit in the bank? $134. So if we're doing nothing, for, I don't know, 6 years, my money grew to that. Okay? That's how we compound, that's how we find compound interest. Alright, geometric sequences are, they are sequences with a common ratio. So you remember how we studied arithmetic sequences? And those were sequences with a common difference. Geometric sequences are sequences with a common ratio. Let me give you an example of a geometric sequence. This is one, 2, 4, 8, 16, 32, 64, blah, blah, blah. Notice that right away, there's no way this is arithmetic because the difference between any two consecutives is not constant. However, the ratio of any two consecutives is constant. Let's pick this one, for example, out of the blue. If I take 32 and I divide it by the one before it, what number do I get? 2. If I take 8 and divide it by the one before it, I get 2. So another way of thinking about this is that as you move along, we go times 2. And then we go times 2. and then we go times 2, and then we go times 2, and then we go times 2. So notice that all the way through, my ratio remains constant. That's the definition of geometric sequences. Now, just like arithmetic sequences, you can write them two ways. What are the two ways you can do it? Remember, one starts with this. Yeah, you can do it recursive, or you can do it what? Explicit. Very good. So I'm going to give you both right now. Okay, the recursive way to write a geometric sequence is this. Tell me what a sub 1 is. So we'll just call a sub 1 as the value of a. And then you know that a sub n is just the whatever the previous term was, which is a sub n minus 1, multiplied by the ratio. That's it. Right? So to get the 8, I just take the 1 before it and multiply it by the ratio. That's what that says. Now, explicitly is a little bit different. Okay, explicitly, a sub n is going to be, any term in the sequence is going to be the first term multiplied by the ratio to the n minus 1. Why do you suppose it's to the n minus 1? No idea? Let me show you. Let's take this one for example, okay? What is my common ratio in this case? My ratio is 2, right? Okay. This is the first term, this is the second term, this is the third term, right? So let's take the third term. How many times have I applied the ratio of 2 in order to get to 8? No, I've only done it twice. So I'm starting with 2 times 2 and then times 2. So what about this one? This is the fourth term. How many times have I had? Yeah, the power minus 1. That's why. So I've applied it 3 times. I have applied the ratio 3 times to get to my fourth term. That's why my initial term and my n minus 1 is in the explicit formula. Okay? Okay, here is a geometric sequence. We're going to write it both in explicit and recursive terms. So we'll start with the recursive, okay? So to get a recursive, we list the first term. In this case, what is the first term, everybody? It's 7. Very good. What's my common ratio, by the way? The ratio is 3. Just pick any term and divide it by the one before it, and that has to be constant. So our ratio is now equal to 3. So the recursive formula says, okay, a sub n is equal to the term before it, a sub n minus 1, times the ratio of 3. So all of this together inside that box is how you would write the recursive formula. You've got to tell me this part. Many students forget to write that part in. Why do I need that part? No, because if I just told you, hey, write a sequence where the ratio is 3.
Oh, you have to figure it out.
We could all write 50,000 different geometric sequences. You got to tell me what it starts with, right? You got to give me that, and then I can give you back the unique sequence. Now, what about the explicit formula? Okay, let's do explicit over here. The difference. I know that a sub n is equal to a sub 1 to the ratio of n minus 1. Okay, the very first term is 7. The ratio is 3, and I have to the n minus 1. That's it. Do not make the mistake of multiplying the 7 and the 3 together. Right? Why is that a mistake to multiply the 7 and 3 together?
Because you have the 3 and minus 4.
Yeah, they don't have common bases, okay, but beyond that, right? Remember, the 7 is a standalone initial term in terms of the sequence. The 3 is that ratio. So you are raising only the ratio to your exponents, not the ratio combined with the initial term. Okay?